Hello students, welcome back to JCE Connect series of lectures. In previous lecture we have discussed about applications of Bernoullis equation. So these are the some applications we have discussed in the previous lecture as how the pressure and velocities are related to each other, and based on that we have discussed these many applications, that is atomizer or a paint sprayer, how they work. Even we have discussed about the ping pong ball, how it stands over the stream of liquid or a stream of air. Okay, when a stream of air is passing. Okay, so these many examples or applications we have discussed in the previous session. Even we have discussed when the two balloons are tied or hanging and a distance apart, when you blow air in between, how they come closer and closer, and this can be explained by the principle of Bernoulli. Okay. So this is also one of the application of Bernoulli's equation. And in today's session, let us again discuss about the Bernoullis equation only, the work and energy. And in this particular example, this I explained in previous session also. Here we know that if we drop a ball, it accelerates downward with an acceleration g equal to 9.81 meter per second square. So here the neglecting the frictional resistance due to air, this is the ball dropping down, and it is coming down with an acceleration of 9.81 meter per second square, and here we are neglecting the frictional resistance due to air, and we calculate the speed of the ball. Here we calculate the speed of the ball. So here we calculate the speed of the ball after falling a distance h. So suppose if we are taking this distance, say this distance h, after falling a distance h by the formula, see that is where is calculating by the formula v square equal to u square plus 2as. This is the formula we are using to calculate the speed of the ball, and in this here we are taking a equal to z, that is acceleration, a equal to z and s equal to h, and the equation could be applied to a falling droplet of water also. Suppose if the droplet of water is also falling down from a distance height, and the same equation can be applied to calculate the speed of the droplet of a liquid. The same law of motion can be applied. So instead of a ball, if the drop of liquid is falling from here, so suppose this is a drop of liquid falling down, the speed of this drop of liquid can be calculated by using the same equation of motion. Same can be applied. This is v square equal to u square plus 2as. This is a formula to be used. Next, a more general approach to obtaining the parameters of motion. Suppose a more general approach to obtaining the parameters of motion, both solids and fluids, is to apply the principle of conservation of energy. This is very, very important principle of conservation of energy. That is, energy can neither be created nor destroyed. So here when friction is negligible, then we can say the sum of kinetic energy and gravitational potential energy is constant. Just look at this picture here. A wall is falling from certain height down. Okay, so here what is happening? One form of energy increasing and other form of energy get decreasing, but at the end when you take the sum together, that is sum of kinetic energy and gravitational potential energy is constant, means energy is not at all changing, it is just transforming one form to other form. So energy, we can say it is conservation of energy. Okay, so here kinetic energy we can write half mv square as we know, and gravitational potential energy as we know the formula m into g into h. So as the ball is falling down, it gains a kinetic energy because of its motion, that is we can write half mv square from the simple law of motion. And also the gravitational potential energy we can write mgh. At this position we can write it is the ball is having a mass m and it is falling down due to acceleration due to gravity. Okay, we can write the gravitational potential energy at this position is mgh. So to apply this to a falling droplet, we have an initial velocity 0. Suppose the same formula, whatever the formula you are having here, equation of motion, if you want to apply this to the falling droplet of liquid, here it is written, to apply this to falling droplet, we have an initial velocity of 0 and it falls through a height of h. It falls through a height of h. So here we can write initial kinetic at this height, at a height of h. What is the initial kinetic energy? 0. At this position, initial kinetic energy is 0. Just look at this picture. So this picture, when the ball is at this position, it will be having a potential energy, but kinetic energy is 0 here. Just look at this picture here. One form of energy is decreasing, other form of energy is increasing. Okay. Then what about the initial potential energy at this position? M into G into H. That is written here, M into G into H. Then what about the final kinetic energy? So final kinetic energy will be half mv square, since it is falling down. When it gains the kinetic energy because of its motion. And what about the final potential energy? 0. At ground level the potential energy is 0. When it is at a height of h, the potential energy is mgh, but the kinetic energy is 0. But when it falls down, it gains energy, that is kinetic energy, because of the motion, that is half mv square. Okay, means just look at these two pictures here, this as well as this. So one form of energy is decreasing, other form of energy is increasing. When the ball is at a height of h, there the potential energy is maximum, kinetic energy is 0. Okay, but at the end when we take, as we know that kinetic energy plus potential energy is equal to constant, that is based on the law of conservation of energy. Okay, law of conservation of energy, that is sum of kinetic energy and gravitational potential energy is constant. Okay, next, so initial kinetic energy plus initial potential energy, can write finally initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential energy. So we can write initial kinetic energy is 0 plus potential energy is what? mgh. So final kinetic energy is how much? Half mv square. We can write here final is 0 here, and initial we can write here 0. 0 plus mgh plus is equal to half mv square plus 0. So what we get the equation, so m get cancels both side. The final equation what we get, the velocity equation. This is the equation we get finally. So although this is applied to a drop of liquid, a similar method can be applied to a continuous jet also. See, since this above equation whatever we have applied, that is law of equation of motion, to the drop of liquid, when the drop of liquid was falling down, okay, so we have applied this above this equation to the drop of liquid. Okay, so the similar equation, when that is the similar method can be applied to a continuous jet also. So let us look this one, just a minute. Continuous jet. So here, so this is the continuous jet. So the jet is coming out of the pipe. Okay, so this is the jet. So if we apply to this one, so what will happen? So we can consider the situation as in the figure, a continuous jet of water coming from a pipe with a velocity u1. Just look here, a continuous jet which is coming out of the pipe with a velocity u1, and one particle of the liquid with a mass m. Just you consider one particle of the liquid with a mass m travels with the jet and falls from a height z1 to z2. Okay, so we are considering one mass of a liquid at a height of z1 and it is falling from z1 to z2. Then the velocity also changes from u1 to u2. Initial velocity was u1, and when it is falling from a height of z1 to z2, see the liquid is coming out of the pipe, so it is coming with a jet. Okay, and initially the liquid particle is here having a mass m. This is having a mass m and it is falling from a height of z1 to z2. It has reached here. So when it is falling from height z1 to z2, similar to the drop of liquid which was falling down from a height of h. So but it is a jet of liquid which is falling from a height z1 to z2. So the velocity will also get changes from u1 to u2. Initial velocity was u1 and final velocity was u2 here. Then the jet is traveling in air where the pressure is everywhere atmospheric. Means as this is the pipe and through the pipe the jet is coming out, and as the jet is moving down like this, okay, so everywhere there is atmospheric pressure acting on it. So there is no force due to pressure here. There is no force, external force is applied here. Only the force is, that is pressure force, that is atmospheric pressure is acting here. That is, there is no force due to pressure acting on the fluid, and the only force which is acting is due to gravity. So this is the only force which is acting on this jet is gravity. Then the sum of kinetic energy and potential energies remains constant as we neglect the losses due to friction here. So we are neglecting the losses due to friction here, and the only, since it is falling into the atmosphere, and the only force which is acting on this jet will be the gravitational force. Hence we can say the sum of kinetic and potential energies remains constant since we are neglecting the energy losses due to friction. Then finally we can write this equation for this jet of liquid. So this equation we can write for this jet of liquid, that is we can write the potential energy here. So at this position, if you consider at this position, say the position 1 here, this is a position 1 and this is a position 2 here. If you apply the above law of motion to this jet of a liquid, so we can write energy at the position 1 can be written as mgz1, that is a potential energy, initial potential energy, plus the initial kinetic energy at this position. I am writing here at this position initial kinetic energy, same this formula to be applied, this one. So I am applying the same formula here. Okay, so initial potential energy mgz1 plus initial kinetic energy is half mu1 square is equal to final potential energy mgz2 plus half, that is final kinetic energy, half mu2 square. So as m is constant, this become, because the mass of particle is constant, then we can get half u1 square plus gz1 is equal to half u2 square plus gz2, because the m is constant. Okay, the m is constant. Then this will give a reasonably accurate result. So the above equation, that is, this will give the reasonably accurate result as long as the weight of jet is a large, compared to the frictional forces. So it is applicable while the jet is whole before it breaks up into a droplet. So this equation is applicable to while the jet is whole before it breaks up into a droplet. Okay. Then one more, the flow from a reservoir, one more just example. You take the flow from a reservoir just like this. So we can use a very similar application of energy conservation concept. So we are discussing about the law of conservation of energy, energy conservation concept to determine the velocity of flow along a pipe from a reservoir. So consider the idealized reservoir in the figure below. So the level of water in the reservoir is Z1 here, and considering the energy situation in this also the considering the energy situation here also in a reservoir, there is no movement of water. So here there is no movement of water, so the kinetic energy is 0, but the gravitational potential energy is mgz1 at this position. So this is the reservoir. Okay, at this position, if you take it, see, I am writing it the position 1, just at the surface, on the surface of liquid, surface of water, just you take the position number 1. At this position, if you take the particle, that is a liquid particle here, a mass m, then the potential energy at this position is mgz1. Okay, if a pipe is attached at the bottom here, suppose if you are attaching a pipe here, if you are attaching a pipe, if a pipe is attached at the bottom, water flows along the pipe out of the tank to a level Z2, a mass m has flowed from the top. So here we have considered the mass m, which has flowed from a top to the reservoir, so the top of the reservoir to the nozzle, and it has gained a velocity u2. So the kinetic energy is now, so we can write here a level of this here, the level of water in the reservoir is Z1. Considering the energy situation, there is no movement of water, so the kinetic energy is 0, but the gravitational potential is mgz1 at this position. Okay, so if the pipe is attached at the bottom, water flows along this pipe out of the tank to a level Z2 at this level here. Okay, at this level, a mass m has flowed from a top of reservoir to the nozzle, and it has gained a velocity u2 here at this position. So say this is 2. The kinetic energy is now half mu2 square, and a potential energy is mgz2. So summarizing, initial kinetic energy here at 1 is 0, then the initial potential energy will be mgz1, then final kinetic energy is half mu2 square here, final kinetic energy, and final potential energy is mgz2. Okay, similar to previous one. So finally what we get, we know that kinetic energy plus potential energy is equal to constant. So what we can write, this is the equation what we can write finally. So mgz1 is equal to initial kinetic energy is 0, but there is a potential energy, so final kinetic energy we get plus final potential energy also we get. So this is the equation finally we get. If you simplify this one, we get this one. Now apply to this the example. Let us take one example. A reservoir of water has a surface at 310 meter above the outlet nozzle, a pipe with a diameter 15 millimeter. So what is the velocity, the discharge out of the nozzle, and mass flow rate? Okay, so just we have simplified this one, that is flow from a reservoir by using the equation of the motion, so like a previous example, and finally we have obtained this equation. And utilizing this equation, let us take one example of this one. So let us discuss discuss about this example. Okay. So very similar example as that of previous. So this is the flow from a reservoir example we have taken. So in this reservoir, liquid is held, and it is here. So we have considered the just exact on the surface of water 0.1, and here we have considered 0.2. So this is we have considered 0.2, and finally we have applied the law of motion. So finally what we have got as, so this is the equation we have got. Just we have applied this one, this equation we have applied, that is kinetic energy plus potential energy equal to constant. So we have applied this one and we have got this one. So now apply this to this example. Just let us take on one example here. A reservoir of water has a surface at 310 meter above the outlet nozzle of a pipe with a diameter 15 millimeter. So what is the velocity, the discharge out of the nozzle, and third one is mass flow rate. Neglect all friction in the nozzle and the pipe. Okay, so this is the example given here. Just utilize the above equation, then calculate these three, that is velocity, discharge and mass flow rate. So here just we can utilize this equation to calculate directly u2 equal to root of 2g z1 minus z2. So this is the equation we are having with us, or else you can use, that is the law of conservation of energy, that is initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential energy. When you apply this one, you will get this equation. So since we have already derived the equation and we are having the equation with us, we can utilize that equation and apply it to this problem here. So u2 equal to, you can write root of 2g z1 minus z2. Since in this for problem this is 310 is z1 is given, so here z1 is given 310 meter height in this reservoir, and sorry the z1 minus z2 is given, z1 minus z2, that is the reservoir water has a surface at 310 meter above the outlet nozzle, means here this one, above this one, from here to here it is 310 meter, means z1 minus z2, here z1 minus z2 is given. Here z1 minus z2 is 310 meter. Then substitute this value here, we get this one. Okay, so that is 78 meter per second. We have got velocity as 78 meter per second square. And one more parameter they have asked, that is the second one is the discharge out of the nozzle, how much the rate of flow is coming out of the nozzle. So as we know, the volume flow rate is equal to the area of the nozzle multiplied by the velocity. This is the equation we are knowing, that is Q equal to A into V, or you can write A into U. So since I have considered U as the velocity here, that is Q equal to A into U. So here the diameter of the pipe is given, you can easily calculate pi by 4 d square area, and you already calculated that. Substitute here, you will get the discharge in meter cube per second. Okay, so this is pi by 4 d square, pi by 4 d square. Then the third one is they have asked you to calculate the mass flow rate, neglect all friction. Okay, so the mass flow rate, how we can calculate? The density of water is 1000 kg per meter cube. So the mass flow rate is equal to density into volume flow rate. Okay, as we know, density equal to mass by volume. Okay, so the mass can be written density into volume. So mass flow, that is the mass flow rate. Density is equal to mass by volume. So the mass flow rate will equal to what? Density into volume flow rate, that is rho into Q. So since we know the density of water, that is 1000, and already we have calculated the volume flow rate, this much, then we can easily get the mass flow rate, that is mass of water per second, mass of water per second. So this is how we calculate the various parameters, that is velocity, discharge and mass flow rate. Okay. In the above example, in this example where we have got mass flow rate is 13.78 kg per second, and we have obtained a velocity 78 meter per second, and discharge out of the nozzle as 0.01378 meter cube per second. So in the above example, the resultant pressure force was always 0, as the pressure surrounding the fluid was the everywhere the same atmospheric. Okay, so since a jet of water which is coming out of the tank and which is discharging into the atmospheric, so everywhere the pressure here is atmospheric, so same, that is the same atmospheric pressure only. So if the pressure had been different, there would have been an extra force acting, and we would have to take into account, that is the work done by this force when calculating the final velocity. Okay, and we have already seen in the hydrostatics section an example of pressure difference where the velocities are 0. In the section, that is hydrostatic sections, where we have considered the velocities are 0 there. Okay, the same I have written here. We have already seen in the hydrostatic section an example of pressure difference where the velocities are 0. Okay, so let us consider in this particular example here, just hydrostatics, consider 2 points. Let us call this is point 1 and point 2, and mark at point 1 the pressure is P1, and at point 2 the pressure is P2, and also mark a height above the datum. Let us take this as a datum line or reference datum. Above the datum, the point 1 is at a height of Z1, and above the datum point 2 is at a height of Z2. Okay, so here the pipe is filled with stationary fluid of density rho. So in this particular pipe, fluid is been filled and it is at rest. So a stationary fluid is been considered, and for this stationary fluid the pressure we have considered as a P1 at point 1 and P2 at point 2, and also the positions. The point 1 is at a position of Z1 from the reference, and point 2 is at a position of Z2 from the reference. And we have considered a fluid of density rho has a pressure P1 and P2 as already told, and also levels Z1 and Z2 respectively. So now what is the pressure difference in terms of these levels? If you want to calculate the pressure difference in terms of these levels, so we can write, so they are same. The pipe is filled with a stationary fluid of density rho, has a pressure P1 and P2, the level Z1 and Z2 respectively. The levels are Z1 and Z2 respectively. So what is the pressure difference in terms of these levels? Then we can say P2 minus P1 is equal to rho into G Z1 minus Z2. Okay, so we can write here P2 minus P1 rho into G into bracket Z1 minus Z2. Okay, or else P1 by rho plus G Z1 is equal to P2 by rho plus G Z2. Okay, just rearrange the terms here. So this applies when the pressure varies but the fluid is stationary. Means in this particular case we have considered the velocity is 0 here, but there is a difference in pressure. But the previous example what we have taken, there the pressure was constant, the velocity was varying. But in this particular case the pressure is different but the velocity is constant. So for that one, this is the equation we are having. Okay, I hope you understood this one. So here, that's why I mentioned here, this applies when the pressure varies but the fluid is stationary. Okay, so compare this to the equation derived for a moving fluid but constant pressure. Okay, so means the previous example what we have taken, comparing this to that, so we get this one. Okay, that is half u1 square plus gz1 is equal to half u2 square plus gz2. So you can see that there are similar form. Just if you compare these two, there are similar form, then what would happen if both pressure and velocities varies? So there is a question here. Suppose whatever the example we have discussed till now, so the first example I have considered where the pressure was, the velocity was the pressure was constant, the velocity was varying. And in this particular example I have considered where the velocity is 0 and the pressure was varying. Then when we compare it, so we can see a similar form of equation. Then here I'm asking what would happen if both pressure and velocities varies. Then if both pressure and velocities varies, then we have a equation for that to calculate, that is the famous equation, that is Bernoullis equation. So Bernoullis equation is one of the most important equation which is useful equation in a fluid mechanics, very useful equation, and it also very famous equation, the Bernoullis equation. And we know the Bernoullis equation, that is this is the equation, the Bernoullis equation. And we are expressing this Bernoullis equation in terms of pressure head, velocity head, potential head and total head. Instead of calling the energies, that is pressure energy, kinetic energy, potential energy is equal to the total energy, so here we are calling it as a head. In terms of head, pressure head, kinetic head, potential head is equal to the total head. And the Bernoullis equation, as we know, by the principle of conservation of energy, as we have discussed previously, this conservation of energy, how it can be obtained, that is by taking the law of equation of motion. I have explained, I have taken various example and explained, that is by the principle of conservation of energy, the total energy in the system does not change. The system does not change, that is total energy does not change, just the energy will get transformed from one form to the other form. So finally the total energy will be remains same. That is the law of conservation of energy, just it transforms from one form to the other form. Thus the total head does not changes. So the Bernoullis equation can be written as P by rho into G plus U square by 2G plus Z equal to constant, or you can write it as a total head. Okay, so this is the equation we can write, and this equation what we call as a Bernoullis equation. So we say that from applying equal pressure or zero velocities, we get the two equations from the section above. They are both just special cases of Bernoullis equation. That is, whatever the equation we have discussed previously, they are both just special cases of Bernoullis equation. And the Bernoullis equation has some restriction in its applicability. They are, means before applying the Bernoullis equation, this is the Bernoullis equation, and before applying this equation it has certain restrictions also, or you can say certain assumption to be made for applying the Bernoullis equation. What are those restrictions? The flow should be steady. As I discussed previously, the flow should be steady and the flow should be ideal and the density should be constant, that is, which also means the fluid is incompressible and the friction losses are neglected here. And the equation relates the states of 2 points along a single streamline, so not conditions on two different streamlines. So on the same streamline, that means it can take the point 1 here and point 2 here, and you can discuss or you can relate the pressure and velocities at these 2 points. Okay, that is the equation relate the states at 2 points along a single streamline. It means it not conditions on two different streamlines, means you cannot take the 1 point here and 1 point at here. Okay, on the same streamline you can take the 2 points and you can analyze the flow. So all these conditions are, whatever the conditions I mentioned, that is the flow is steady, density is constant, that is incompressible, friction losses are neglected, the fluid should be ideal. So all these conditions are impossible to satisfy at any instant in time, means in reality it is highly impossible. Okay, so fortunately for many real situations where the conditions are approximately satisfied, then the equation gives a very good results. Okay, so whatever the restrictions the Bernoullis equation is having, so it is highly impossible to apply in reality, but for some of the fluids can be applied and can be analyzed the fluid flow. Okay, and here we have considered at any cross section, means as I said, the Bernoullis equation can be applied for the 2 points here. So it can be applied for a single streamline at 2 points, point 1 and point 2 here. So wherever you take the section here, 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 it can be applied section 1, 2, 3 like this. Then whenever you are applying the Bernoullis equation at various sections, then it can be written as total energy per unit weight at 1 is equal to total energy per unit weight at 2 from the law of conservation of energy. So the total energy at various section will be remains constant according to the Bernoullis. Section 1, 2, 3, whatever sections you are mentioning here. So means the energy, fluid energy at passing through section 1 is same at 2, same at 3, like this it goes. Means it can be written total energy per unit weight at section 1 is equal to total energy per unit weight at section 2 is equal to total energy per unit weight at section 3, like this it goes. Or else you can write, instead of energy you may call it as a head, total head at 1 is equal to total head at 2, like this you may mention. So that's why I written here pressure head, velocity head, potential head and total head. Instead of calling it as a total energy, you can call it as a total head also. So when you are applying a Bernoullis equation at section 1 and 2 can be written at section, you need to write the total energy. So total energy consists of pressure energy, kinetic energy and potential energy. So in that form if you want to write, so we know the Bernoullis equation. So since we are applying for section 1, you have to write P1 by rho into G plus U1 square by 2G plus Z1 at section 1. Similarly at section 2, P2 by rho into G plus U2 square by 2G plus Z2, like this you can write. Suppose one more section is there, you can write P3 by rho into G, P3 by rho G plus U3 square by 2G plus Z3, like that it goes. Okay, so this is how we can write the Bernoullis equation for two different sections. Okay, so 2 points joined by a streamline. Okay, next. Okay, this is the Bernoullis equation, but this equation I mentioned it, this is the equation energy per unit volume. This equation, this is the per unit volume. This equation will be per unit weight, total energy per unit weight. Okay, just rearrange the term, you will get the per unit weight. This is per unit volume. Okay, so here as I applied that 2 points, this is the equation we get finally. Okay, so at section 2 means this is the pipe we are applying at section 1 and 2. Section 1, section 2, like this. If you apply at section 1 and 2, we get this equation like this, and this equation assumes whatever the equation we have written between the two sections, it is section 1 and 2, this equation assumes there is no energy losses. So whatever the equation we have written here, so here we are not even considered the energy losses here, that is from friction. Means whenever the fluid starts flowing, there will be a resistance. That resistance is because of the fluid friction. Okay, that is the frictional force. Okay, then hence there will be a losses in a fluid. So we are neglected that losses or energy gains. The equation assumes no energy losses or energy gains, that is from the pump. Means you are applying a pressure force for the liquid to lift above. To apply that pressure force, so we have connected a pump to lift the water from lower elevation to higher elevations. Means we are in this case there is a gain in the energy. So, okay, liquid gains the energy. Okay, so in this case this equation assumes no energy losses or energy gains along the streamline. So it can be expanded to include these simply by adding an appropriate energy terms. Okay, means if you want to include the energy losses, the total energy per unit weight is equal to total energy per unit weight at 2 plus loss per unit weight. You have to include loss also. Okay, so like this. So at section 1 this is the equation we get, at section 2 this is the equation, plus H means energy loss. So we are including that term also. So if the fluid is ideal, there is no question of fluid friction, hence there is no losses. The loss will be 0 in that fluids, that is for ideal fluid. But for the real fluid there will be a friction, hence there is a loss, hence you need to include this term, that is H, loss per unit weight. I hope you understood this one. So while solving a problem you will understand. So when this equation, when we apply, this equation is useful for the real fluids. Okay, so this equation is useful for the real fluids and this equation for ideal fluid. So remember, this equation is for ideal fluid. Ideal fluid. And this equation is for real fluid. Okay, so ideal fluid means no losses. This equation can be applied for those fluids which doesn't have any energy loss, that is ideal fluid. And real fluid means with losses, means these fluids will possess viscosity, hence there will be a losses, that is frictional losses. And for a frictional losses, this equation can be applied to analyze the fluid flow, and for the no losses, this equation can be applied to analyze the fluid flow. Okay, I hope you understood this one. So in the next session we'll take some examples and we'll solve, that is with loss and without loss. Okay, so that is the problems on Bernoullis equation. Thank you.